Yeah. Um, Hi, good morning, everybody. My name is Punnoose. My paper today is New Features for Discriminative Keyword Spotting. Um, and I am presenting this from India. Um, so this is my presentation overview. I will explain what is keyword spotting, what is discriminative keyword spotting, and what approach that we took, and what are our results, and some future work, and conclude the paper. So keyword spotting is basically spotting a particular keyword, spotting a particular word in a speech stream. So it could be used for wake-up word detection in devices. It could be used for sentiment analysis. Mostly it is used for audio indexing and retrieval. So there are broadly two approaches. One is a large vocabulary speech recognition engine based system, and other is a keyword specific model based systems. So in a large vocabulary keyword spotting system, it would be like we'll be using a general purpose speech recognition engine. Mostly it will be HM based context dependent form models. White will be decoding scores at the word level will be used as the keyword scores, and language model contributes heavily for the recognition of the keywords. Now, if the case is like if the keywords are coming in particular domain, then you can actually use a specific language model, appropriate language models made from that particular domain for more record. Now, the good thing about word level HMOs is that it is mostly it will actually capture all the co-articulation, all that kind of stuffs. But one negative thing is that it may not be. I mean, the states of the HMM may not be corresponding to interpretable phonemes, and mostly it is generative models. And sorry, I think slightly. Yeah. If it is a keyword specific model, we can actually use word level HMMs. But again, the problem here is that uh, accuracy may not be that good actually, and it will be mostly generative. So the information of another particular keyword is actually not used while we are actually trying to train one keyword. And if it's a word level HMM, we don't really use a language model; it's purely acoustic. So but one good point is that only you need a word level alignment, which is actually a good thing. Now, discriminative keyword spotting is something based on the paper by Joseph Cassett, David Granger, and Sammy Winju. This is actually a pretty old paper, 2009. So there will be a scoring function for every keyword, w.phi xss. Phi is actually a vector valued function, and x is a acoustic phonetic variable, and s is an alignment sequence. So what we did is that what we took this idea, we changed this x's into a set of another variables vk, x, p, and f. So vk could be the variables like the distribution of the ideal duration of the keyword, ideal dictionary entries of the keyword, number of voice segments, distribution of the ideal duration of the voice segments, all those things. X would be the, and we actually use a frame-based phoneme classifier along with a pitch detector for this particular purpose. So X is actually the variable which actually represent the decoded phoneme string sequence with the corresponding probability sequence P for an utterance of length T frames, and F is a sequence of pitch values. And we map it. This is actually a vector function. Phi is actually a vector function. We map this variable to a point in R5. So in training, what we are doing is that we have for every keyword we have instances of keyword where instances where we have the keyword present, and instances where we don't have the keyword, which is termed as the negative tuples. So this is the general training thing, training algorithm. This is basically more similar to a online discriminative margin based training. So we have a weight vector corresponding to each word, each keyword, and the tray, and at the I-1 stage, the weight vector is represented as a WK I-1. K represents the keyword. So what we are trying to do is that at one point in training, the I-1 stage in the training, we get a dot product, a maximum dot product with the negative acoustic vector. Means with the speech segments where the keyword is not present. And this is what we term as a worst possible negative acoustic tuple for a keyword at the training instance I-1. In the ith instance, this has to be penalized. So this is the so we define a delta I variable as the difference between the worst the difference between the worst acoustic negative tuple and the present positive acoustic tuple. So this is a simple optimization problem which is simply a L2 norm. This is actually somewhat similar to the SVM training objective, and it has a closed form solution of WKI is equal to WKI minus 1 plus delta I delta I, where this is actually hinge loss function minimized. So minimize minimum of a 1 minus WKI minus 1 delta I over delta I squared. So A is the complexity accuracy parameter. So what we this is the fundamental training algorithm. Online this actually works in an online fashion. If each instances of a keyword is actually passed to this algorithm, and W is actually trained. A simple online learning algorithm. Now, what we have done here is that we defined a set of feature functions. So for that, we used a frame-based phoneme classifier along with a pitch detector. So we define this phi. We define this phi vector in terms of this pitch detector and frame-based phoneme classifier. So phi1 is the percentage of relevant phonemes detected in a sequence index in the total number of phonemes of the dictionary entry of the keyword. So this captures the relevance of the phonemes in the piece segment to the keyword. Phi2 is the percentage of the relevant frames detected in the sequence out of total. The difference between these two is the phi1 is actually the percentage of phoneme detected. Phi2 is actually the percentage of the frames detected. Now, phi3 is based on an observation that for a frame-based phoneme classifier with a softmax output, the density of the softmax probability for true positive and false positive phoneme detections are different for different phonemes. So this is actually the density of a softmax probability of particular phoneme F, where for false positives and true positives. This is actually made from a frame level phoneme labeled database. This is for another phoneme A. And you can actually see that there's a slight difference. This is the difference actually we are trying to get. From this difference, what we are trying to do is that from this kind of difference, whether can we predict which phoneme it is, or if we say that this data is actually coming from one particular phoneme AA, how much it is true. This is what we are trying to get. So phi3 is the average ratio of the density of frames of as probability of true positives or false positives of whole of the sequence averaged. Now what phi4 captures is how well the total duration of the detected voice regions in the speech when matches the ideal total voice duration of the keyword. So we know what keyword we are trying to get, and we know how many voice regions are there, and we have a rough idea about like what's the total duration of the ideal voice duration of the keyword. We represent it using a normal distribution, mu voiced, sigma squared voiced. Similarly, what phi captures is how well the duration between the voice regions at the starting and end of the speech segment matches to the ideal duration between the voice regions at the boundaries. So we expect that there is at least two voice regions in a keyword, and we try to get the duration between the voice regions in the keyword, and we represent this duration using again a normal distribution. Um, so this actually mandates that the keyword should have at least two voice segments. And this is again coming from a label data. We take the label data, we label it, then we will figure out, we run it across the pitch detector, then we will get to know the pitch at every at least 50 milliseconds. Then we figure out like how, from the pitch we will get where are the voice regions. We do some kind of stylized pitch stylization to get like how many voice segments are there. Then we figure out the difference between the duration between the first voice and the last voice region. We fit a normal distribution here. So these are the 5 feature functions that we use for the keyword detection. Now, the problem that we are trying to when we are trying to train the algorithm for every keyword, the negative data is typically very much higher than that of the positive data. So there's one thing that we can do. We can randomly choose the negative segments where keyword is not present, and for this worst acoustic vector computation, we need to take a dot product here with respect to all the negative acoustic data. Now the problem here is that this is actually too much computation involved, because if you take any database, the number of positive instances will be very low actually compared to the negative instances. So so taking this dot product each and every time while we are trying to run the algorithm, I mean, while during the running time, during the testing time, is actually difficult. So what we have come with an idea is that we take the convex hull of, because this is actually this 5 is a vector function which is actually mapping this variables into R5. So what we do is that we take convex hull. This is actually finite set of points. We can actually take a convex hull of all the we can actually take convex hull, and we will get to know the extreme. We will get to know the extremal points in the convex hull. So there's actually a property which says that you can actually take the dot product. We can actually take the dot product of the convex hull if we want to find the maximum dot product, or if I want to find the maximum dot product, the point where the maximum dot product, that point will be in the extreme. That point will be one of the external points in the convex hull. That point will be one of the points in the extremal point in the convex hull. So you don't actually need to take the dot product with respect to all the negative data. We can actually take the dot product with respect dot product of this WKI minus 1 and only the external points in the convex hull. So what we have done is that we have actually used the Oxford data, which is freely available. 40 hours of data, 40 hours of Oxford data is actually forced using Cali, a multi-layer perceptron, baseline multi-layer perceptron with architecture 351, 1000, 1041 is built in is the QNet with the PLP coefficients feature. This 351 is actually coming again 9 frames, each frame corresponding to 39 features. PLP feature delta, double delta. So 39. Left 4 frames, right 4 frames, total will be 9 frames, will be 351. 351 will be the size of the input. Standard English frames are used as a target. 9 frame PLP input for each frame corresponding to 25 millisecond to 50 millisecond overlap. The classifier output is a probability vector of size 41. This 41. Each component corresponding to a phoneme. The phoneme corresponding to the highest probability is treated as a recognized phoneme for that particular frame. For voice range identification, what we use a simple autocorrelation based pitch detector, which anything outside the 40 to 600 hertz is discarded. Pitch values are computed on a 50 millisecond time window and the boundary adjusted with output of the frame classifier. So this both actually gives us all of these variables: VK, XK, PK, FK. This VK variable is actually not actually coming from a pitch detector and the frame is phoneme classifier. Is actually the variable which is related. This is actually acoustic phonetic characteristics available, like how many phonemes are there, how many voices, how many ideal voice segments are there in the keyword. So what we are trying to do is that we are actually trying to we are actually trying to map this variable, which is more of like a invariant VK, which is like an invariant variable, to the incoming acoustic variables. These X, P, and F are the true acoustic variables. This variable, this V is also an acoustic variable, but the point is, it is actually an intact variable. It's not going to change actually. I mean, like the dictionary and the dictionary the dictionary entry of that particular keyword, that will not actually change. Now, so then 5, 3, 5, 4, and 5, 5 needs distributions. 5, 4, and 5, 5 needs distribution and normal distribution. So for that, we use under 20 hour of works for the data to learn the parameters in 5, 3, 5, 4, and 5, 5. Then another 20 hour of data is actually run through the baseline classifier and pitch detector to get the D meta. D meta is what XPF, which, and again, D meta is labeled at the word level. Positive and negative training segments of each keyword are generated. 10 keywords are chosen depending on the frequency, duration, presence of voice regions in the boundaries. So this would be the RC curve for this keywords: Australia, assistance, schedule, powerful, mysterious, 100, daylight, fighting, quickly, stop. And this is actually plotted separately, independently. For each and one of these keywords, we learn a weight vector. And when we are while we are testing it, we test it in separately. Means while we are testing Australia, we merge all the other data along with the then all the data along with the negative instances into the negative data for this Australia keyword, and we get the this false positive rate and a true positive rate. And this is actually the number of extremal points in the convex hull out of 20,000 negative instances. Means out of 20,000 negative instances for the word Australia, what we need is only 126 instances for getting this worst acoustic vector. So almost like an order reduction in a computation. So the reason why we want to have this kind of reduction in computation is because the positive points are, yeah.
Sorry to interrupt. You have 2 minutes, including questions.
Yeah. And we actually compared this with the next lattice keyword spotting purely from Caldi, and this is actually performing better. I mean, Caldi keyword spotting is actually performing better compared to the idea that we proposed. So in that sense, it's actually a slightly negative result. So concluding, I mean, we made a set of 5 robust features derived from a frame classifier and pitch detector for the discriminative approach to the keyword spotting problem. Mechanism by which the feature function finds a correspondence between the keyword specific variables and the speech segment is discussed. A computationally intensive operation in keyword training is identified and a solution is presented. The proposed approach is implemented with a set of 10 keywords with a Oxford dataset. A lattice-based keyword search is implemented and Galilei with the same dataset. Results are compared. So this can be actually used to incorporate any other, feature functions derived out of any other features like formants or acoustic phonetics or phoneme specific spectrograms or anything like that for a better keyword accuracy.